So I've written down some quick recap. I guess everyone knows what a Diophantine set is, but there are some different definitions lying around. For me, I don't use any parameters unless you add those as constants to the language. I also normally don't use or statements, only the ends, because like if you write it in your language of rings, you usually only necessarily need the more polynomials. If you're working over a ring and your language is the language of rings and you don't add any weird predicates, they're all equivalent. So I'm not going to worry that much about it. Language of rings, for me, doesn't contain the minus function. And for Hilbert's 10th problem, we ask if there exists some algorithm to decide this right-hand side, or in the more logic statement, types or formulas of this type. Well, my title already consists of two parts, so I'll first do the Diophantine map part, and then the second part. So the first paragraph is Diophantine maps. And like the motivation for this is that we've seen that Diophantine sets nicely capture the structure of Hilbert's 10th problem. But we also want to have some morphisms, some way to take this Diophantine sets to other rings or other structures with some language. And well, we can make a very easy definition for that. So I take R1, L1, and R2, L2, and I have some map D. Yes, these are L's. These are the matfrag L's. And this is a Diophantine map. If we have for all S in some power of the first ring, Diophantine. We also want D of S, where we apply the coordinate twice to make sense of this, is also a Diophantine set.
Question. Do we want this for every K, or for one specific K that's good enough to make it a Diophantine map?
For all K.
Okay.
Yeah, that's important. For all S, for all K. I guess the K goes. And well, we also have seen that if you want to reduce, or maybe you haven't seen in the previous talks, people may have seen that sometimes you don't really want one element here to correspond to one element there, but you want some equivalence relation on that. And so if this sure. And we have some map D now going from R1 to this modeled out space. We can still say something about being Diophantine. Oh wait, I should have said that's the projection. I call it phi. Then D is a Diophantine equivalence map, or equivalence comes from the equivalence relation. If, well, we cannot longer say that D of S should be Diophantine because we don't have any Diophantine sets in here, but we can just take everything that will map to that. So if for all, I guess for all A again, for all S Diophantine, I will note the resulting thing by d bar of S. This consists of all elements in R2 to the K such that I of X is in the image of D.
Excuse me? I'm very confused about this notion. So if D just sends elements of R1 randomly to, say, 0 and 1, is this a Diophantine map? I mean, the image of everything is Diophantine.
Yes, that's a very good point. So yes, this allows some very weird things, and I will come later to a little bit more precise notion, which is effective version of this, which says that like does it just random sending it to 0 or 1 is like not good enough to say nice things about Hilbert's tenth problem. But yes, it is indeed a diagram.
So this doesn't correspond to anything we should know?
No. I will do at some point later on, if I have introduced some more stuff, I will do some connections with interpretations.
Thanks.
Yeah. So I guess I should... Well, examples. So, well, this is kind of an annoying thing to check, unless you make some weird examples by sending everything to sort of specified Diophantine sets, you don't know anything. But the good thing is that it's not actually as bad to find Diophantine maps.
I'm sure you still want to write this Diophantine.
Yeah, I do. I write Diophantine too many times. Same setup. We let D go from R1 to R2 mod some equivalence relation. Note that like Diophantine maps are a special case of the equivalence version where you just take the equivalence to be equality. So I'll in the next things only do this one. And let it be injected. This is a very key point of this theorem, otherwise it completely breaks down. We have that D is a Diophantine equivalence map if we have that for all constants in our language, the corresponding set is Diophantine. For all functions in our language, we need that the graph of that function is Diophantine, or the image of the graph of that function. So, D of the set of x, comma, f of x, where x. Lies in the first thing. We want all our relations to behave nicely. And then there are two more things that we need to ask. Depending if you see that the relation is in your set or not, you already check it here or not. So we want that the image of our first ring is Diophantine. And this is equivalent to the equality being Diophantine. I guess I'll cheat a bit. The last thing we want is that our equivalence root. Oh, wait, no. Either one of those two things needs to hold, so you want that the image of your equivalence relation wait, not the image. You want that your equivalence relation behaves well, so you want the set of x comma y in R2 squared, for which x is equivalent to y, to be Diophantine, or you only want that in the image. That's also good enough. And well, this last thing becomes trivial if we have the equality as our equivalence relation. And what you basically do is some induction on the terms to show that those maps or graph of a term is still seen as a function is still Diophantine, and then you can like combine everything together. And what this gives us is that like not only we know that if you have a Diophantine set, it still is Diophantine in the stupid you send 0 or 1, everything to like 0 or 1 randomly. But you can also like get the formulas that describe your image from the formulas that describe your set S. And so I'm gonna do a not careful definition. If you have an algorithm that's given the equations that describe S give the ones that describe D bar of S, then D is effective. And well, then we can do the examples. One of my examples was kind of already stolen. So if we take the map D going from Z with the language of rings to F2 with the language of rings, and we just map any x to 0. Then we have two options for the image of our Diophantine set, or basically for any set. We either have that it is singleton 0, if S is not the empty set, or we have that it's the empty set if S is empty. So we see that this is Diophantine, but you see that it is not effective, because we can always figure out in F2 which of those two we are, because we can just check all the options. Which means that if we could effectively go from some description of S to a description of one of those, we can then also decide it, but that's impossible because Hilbert's 10 problem over Z is undecidable. So this is Diophantine. But not effective. Any questions until this point? No, well, we did all this trouble. Oh, there's a question.
So you chose to have it be, first of all, Diophantine maps, they also have to be ring homomorphisms, right?
No.
Oh, they don't?
No, they absolutely don't.
Oh, okay. So is there a reason that we chose F2? Like, theoretically, this result works for any, like, it doesn't have to be F2. Like, that D doesn't have to be going into F2 because we don't require anything about, we're not using anything about, like, surjectivity, are we?
No, so it also is not surjective. I only lose for the fact, to prove that it's not effective, you need it to be a finite domain.
Okay.
Just F2 is the easiest finite domain.
So if I want effective Diophantine map for this example, then which is the effective one?
It doesn't exist.
Okay.
Yes?
So I wonder, is there any reason why we don't use the graph definition? Diophantine.
Wait, what is the question?
Is there a reason why we don't use the graph definition of Diophantine map? The usual thing we do is some function in Diophantine if the graph is Diophantine, but why we don't use that?
Because then you need a language on R1 times R2, which you do not necessarily have. I guess you can also construct it such that this works, but that would be a hassle. So well, then we have the connections with Hilbert's 10th problem, because we did all this stuff and now we want to know that it actually works. So, well, same setup. Reduction theorem. Or at least that's what I tend to call it. So we have some ring R1 and L1 structure, I should say. And we assume that L1 and L2 are finite. You can relax that assumption a bit, but then we get technical details, which I will skip now. And so if we have the R1 to R2 modern equivalence relation, a Diophantine equivalence map, and we know that Hilbert's 10th problem over the first ring, no, second ring, R2, L2 has a positive answer. Then so has Hilbert's 10th problem over the first ring. And wait, I should get rid of effective here. Which is kind of the key point. I guess I can. I cannot write anymore. So the idea is that we're just gonna build this algorithm. And so if we have some statement, say phi, some statement, let's say that this phi. In our first ring, what we're gonna do is we're gonna build a Diophantine set out of this, because otherwise we can't use the Diophantine map. So what we just do is we take all the x's, just one, such that phi y holds. It's a bit of a silly set because it's either empty or everything, but that makes it nice to work with. And then we have this explicit formula, so we can use our algorithm that I just did not properly define, but is an algorithm, to describe d bar of s by some formula, let's say d of y, which might take more variables and everything, but that's fine. And we can look, we can check if 0 is in this set, because we can solve this type of equations, or we can better say check if some element A in the image of 0 is in there.
Can I wrote the set of x in R1 such that phi of y?
Yeah, so phi of y is some statement. Say there exists some square. Some things such as, it asks for a solution of y squared equal to 1. And then I just make the set of x's such that there exists a y such that y squared is equal to 1.
Oh,
So this does not involve any x's.
oh, I see. So it's really.
It's really a stupid set.
Okay. I see. So this is either R1 or it's empty. That's what you were saying.
That is what I'm saying.
Yeah.
And so now we just check if some certain element is in there. And we can do that by our algorithm for R2. Because we have this nice description. And well, if it's in there, then the set was not empty, so then we had a solution before. If it's not in there, or we don't have a solution, so the set was empty. So this decides. And we can make this all precise, which I'm not going to do here. And then I promised you some connections with interpretations. So I discovered those after I've written all this stuff. And it turns out that it's like mostly equivalent. So basically if you have it's very important that you have an injective Diophantine map. What you basically can do is you can build an interpretation out of it. And so the interpretation will go exactly the other way around. So first we're going to specify the domain of our interpretation. So we can find some Diophantine subset of R2. And so the domain and it basically goes from the image of R1 back to R1. And what we do is we take some class here. We take some element here. We can look at its class, phi of x, and then we can take the inverse image to end up in R1 again. And because Diophantine, well, if you are in the case that like you can also use or statement and everything is equivalent, we have that. I should write positive. A Diophantine set is basically a positive existential definable set, so that like everything, what you need for an interpretation will follow from the reduction theorem. That it's, or it makes that you, if you try to do this the other way around, then the definition of your interpretation will give you the conditions of the theorem that's up here. Which gives you that it's a Diophantine equivalence map, and for the other way around, all the things that you want to be positive, existential, definable are Diophantine sets. So those are interpretations. This is a bit fake, I'm not that used to interpretation, so I hope it's clear. short for this board. Are there any questions about the first part? Then I will move on to my second part. And so I promised you some non-commutative rings. And I actually looked at like two types of families. And the first one is the twisted polynomial ring. And well, some of its variants. So I guess I should first tell you what it actually is. And so let K be a field of characteristic P, and we take Q a power of that P, then we will denote the twisted polynomial ring with this curly brackets and tau. And as I said, it is just your usable polynomials. And we also use the usual addition. But for multiplication, we have another rule. So normally if you just want to move your A of your field to the other side of the tau, you just do that. But now you get a little penalty for that. So you should raise your element A to the power Q. That's because I'm working in characteristic P, this is nicely well-defined ring. And we extend this rule linearly. I guess I should make some more definitions. First we'll do notation. So I always assume that K, P and Q are on above. I write A for the polynomials over FQ, and I'll write F for the field fractions of that. And we're going to say that K has some A field structure. If there exists some FQ algebra homomorphism gamma from A to K. And we don't require this thing to be injective. So if Q is equal to P, we also always have this. So we can namely take FPP, which is map it to FP, and since we are directors to P, we can embed this into K. This kind of things are allowed. And the reason why we do this is that twisted polynomial rings play a very important role in the setting of Drinfeld modules. That's also where I first saw them appearing. And Drinfeld modules use this structure in their definition. And we're going to use these Drinfeld modules to solve Hilbert's 10th problem over this twisted polynomial rings. So from now on, I will assume that K has such an A-field structure. Well, a Drinfeld module is a FQ algebra homomorphism phi. We start in A and we go to the twisted polynomial ring. And we wanted to respect this A-field structure, which means that we want that 5t, which like fixes our whole thing, which I will denote as is usual in this field with a subscript t. And I want it to be gamma of t in the first constant term. And then I have some g1 of tau to gr of tau. I want that gr is non-zero, and then r is the rank of phi. Okay. There are a lot of definitions, I know, so I'll do an example. Which will hopefully make it a bit more clear.
You want that to be tau to the r? You want the last...
Yes, I do want this to be tau to the r. Thank you. And so the example is the Carlitz module, which is kind of the running thing we were also going to use, or what you always can take in mind. So we take R to be 1, it's the rank 1 example, and to be even more easy, we could take G1 also to be 1, and this now nicely fixed for 5t to be gamma of t. So this still depends on like which field we're working in and which A-field structure we have on that. And if we want to know what 5t squared plus t is, well, it's an FQ algebra homomorphism, so we get phi t squared plus 5t. And now, if we want to work out this square, we need to like pay attention that we have this non-commutative t here. So we get a gamma of t squared. One is the nice way around, and the other one appears to the right of it. So we still need to do it to the power q. And then we can like simplify everything into one. It's not very illustrative, so I'm not going to write it down.
So is that tau squared terms?
Yeah, there is definitely a tau squared term missing. That's why you should never do equations out on the board. It always goes wrong. Anyway. So So, well, I promised you that we're going to solve Hilbert's 10 problem for the just polynomial rings. So, let's find the rank 1 differential module. If you want, you can just take the Carlitz module. Yes.
So I'm a little confused. So what's the definition of a Diophantine module? Is just a module that...
It's not a module.
Or
Yeah.
it's a map?
Yes.
It's a map that its image, you can realize it as like a, just a...
Yeah, so the thing is, you can see...
powers of tau?
Twisted polynomials also have an interpretation, or like have an isomorphic ring, which is the FQ linear polynomials. And like, if you use that and then like go to your, that like allows you to set a different module structure on K. Like K already has an A module structure by gamma, multiplied by the element. But like you can use a Drinfeld module to put a completely different module structure on this K. That's why they're called Drinfeld modules. Which is like an annoying name because I don't want to explain how you exactly do that. And for our thing, we only use the fact that they are FQ algebra homomorphisms.
So, but then I'm confused. Why do we have that phi of t is equal to this thing that goes up to only powers of tau to the rank, but there our rank is 1, and we go up to powers of tau squared?
Because this is phi of t, and not phi of t squared. So here we're calculating phi of t squared.
Oh, okay.
And that gives us the tau squared.
Okay.
Yes. So we take this rank 1 Drinfeld module. We need to give some languages to our rings. So we give A the language L subscript T, which is just the language of rings, with the extra constant T. And we give our twisted polynomial the language L gamma and tau, which is again the language of rings with 2 extra constants, namely tau and gamma of t. And you can get rid of the gamma of t by making a different Avesot structure, but for now we're just gonna keep it here. And then I is a Diophantine map. And Hilbert 10 over the twisted polynomial ring. I already changed the orders. Well, anyway. Is undecidable or has a negative answer depending on your formulation of Hilbert's 10. Talking too much. I guess that's the thing. Of giving a talk. You're talking, yeah. So, well. Yeah, so I'm going to do the proof for you, or more a proof sketch. You first notice that phi is injective because we have that this GR is not, or G1 is not 0, which means that we can use the theorem that tells us when maps are Diophantine. And then we're going to check all those conditions. Well, phi of 0, 0, that's nice. Phi of 1, that's also nice. Phi of tau, phi of our extra constant t is gamma t plus tau. Well, we just added those 2 constants to our language very conveniently, so that also good. Then we have the interesting part, So if we were gonna look at what the image of A is, you can see, well, I guess you can really easy. You can believe me that this is the elements U in the twisted polynomial ring, such that U times 5t is 5t times U.
Can I ask a question? Are you assuming that the leading coefficient of 5t is 1, or
No.
then why is 5t equal to the m of t plus tau then?
I guess I am assuming that.
Okay.
Yeah, I guess at some point I changed to a rank 1 Grunfeld module, which I should probably have never done.
So, okay, so maybe we
Yeah.
just think
The
about
Garnish
parallax. Okay.
It's the problem if you look too long at this kind of things, you don't see what you write anymore. Yeah.
So in this, T is just any element of A?
It's the generator of the polynomial. I write my polynomials at Q of T.
Oh, okay.
Yeah. No, it's not any element. And this follows from a theorem in Grunfeld modules that says that this image is an A module of rank at most R squared, which is in this case 1. So
The commutative.
But the nice thing is you see this kind of commutators appearing here, which we'll also have later. Or not, maybe. I don't know how fast I'm going. And then we have that phi is a ring homomorphism, which means that also the graphs of plus and times are fine. Okay, just back into the graph of the other plus and times. And then we use the reduction theorem. I guess we can squeeze that in. Because those things give us that phi is Diophantine, and then we have by by work of Dana, we know that Hilbert spent problem over FQG for LT is undecidable.
So I'm just saying A is a quantifier clearly definable in there. Because
Yes.
you have constants for gamma t and for tau.
That's true.
Most 15 minutes.
Yeah, I know, but I'm like figuring out what I'm exactly gonna say. But I guess I'm going for a little bit shorter version for this. And so well, I guess the first generalization of Hilbert's 10 problem from Z is to ask Q. Well, that's kind of hard. But in the characters P case, a lot more is known. And so we can like do the same thing. There are some slight difficulties here, because we have a non-commutative ring. So our general construction of a fraction field does not longer work. Because if you want to multiply some A divided by B times C divided by D, well, you first have to ask yourself, is this B inverse to the left or B inverse to the right? Well, you say, okay, we decided to do that way. Then I want to write this as some R inverse times S again. And which means that I need to move this D inverse to the other side. And so this is like not always possible. Your non-commutative ring has to be a little bit nice. But it turns out that these rings are nice enough. And so we get a so-called left division ring of fractions. Which is this way too long word. And basically it's over ring S. Such that for every x in S, you can write x as R inverse times S, where R and S are elements of your ring. And we want that all non-zero are invertible. And you are gonna believe me that this exists, because I don't have time to explain. So K-tau is the left division ring of fractions. Of the twisted polynomial ring. And probably not surprising after my introduction, we have this nice map phi, and we can extend it to go from the field of fractions of A to this left division ring of fractions. Well, in the obvious way, we define with that phi is a ring homomorphism. So in this image we don't have to worry about which side we set things, because all the phi's will commute. I guess you should also write a statement.
What was that? What was that?
F is the fraction field of A.
Oh, I see. Okay, good.
Yeah. And so phi is a Diophantine map. Hilbert's 10th problem. Over the twisted polynomial ring, I forgot to say we use the same languages as before. So we add the constants tau and gamma to this one, and the constant t to this ring, and then we get a Diophantine map, and this thing is undecidable. And there are kind of two main differences. If you check the constants, same constants still work. If you want to take a look at what the image is, it does still work, but it's absolutely not trivial. So this is still the image. This is still all the elements now in our bigger ring that commute with phi of t. And the way you can prove it is that if something if some a divided by b commutes with phi of t. So, then they have like the same penalty if you commute with this thing. So then there exists some a and b in normal one, such that a so like if you want to switch a and 5t, you can like have a b in front or have an a in front for one of the sides, and we have the same for b. And if I properly defined like how you construct this ring, that is like what you get out from writing down this definition. And then you can show that all the elements that satisfy this relation, that they have the same, well, right actually down. And so we have that there exists some k in your ring, such that this is the set of elements that have like the same. Wait, the b is on the wrong side. This same penalty for commuting with phi of t, and because you have this, then you can like this k get cancelled. So you're indeed in that set. And well, then the other key difference, well, still ring homomorphism, that's nice, but we start with a different ring, but also this is not a problem, because this works by phi-das, and for characteristic 2 by Fidela is that Hilbert 10 over FQ T with LT is nicely undecidable. I promised that I had 2 families of rings, but I'm only gonna do 1. But I'm gonna give you 1 extra example in that ring, which I'm gonna properly explain. So now we've looked at the field of fractions, and like the other thing you can try to do is power series or Lorentz series. And therefore we don't need any wacky constructions, we can just write them down. And this still has the same multiplication rule, which we can extend linearly again, and that just gives us nicely a ring. And the same for the Lorentz series. But now we can start at some arbitrary integer n. And well, you can notice the pattern, but this time it's a little bit unfortunately, because we can still extend phi, but now we start in FQ double brackets t, square brackets t first. Or the Lorentz series field. And then it's again a Diophantine map. But that's where it ends. Because we don't know, we don't know indecidability. And under the conjecture of resolving singularities, we know that Hilbert's tent problem is decidable over those rings. So that's kind of sad. So, well, not gonna help you. But we've seen Diophantine maps can also transfer the decidability results. So maybe you can ask yourself, well, is this twisted version really harder? Yes.
So are you saying that only the top one is a Diophantine map, or are you saying that the...
Oh, both of them are Diophantine.
Okay.
I'm just very lazy with writing.
I would be surprised if the top one was Diophantine and the bottom wasn't, but it would be possible, I guess.
Yeah. But well, if K is already very complicated, we don't have any hope of like being this ring being having a decidable Hilbert's tent. But we can restrict ourselves. So if K is some finite field fq to the n, and if you only use fq, you get everything mapped to the power q doesn't do anything. So we raise it to an extra power fq to the n. Then Hilbert's tent problem over fq to the n, double brackets tau. Well, we still need the constants tau and the constant gamma t, but we also now need some extra constants to be able to nicely talk about all the elements in fq to the n. So we add two extra constants, one generating fq over fp and the other generating fqn over fq. But I guess adding more constants only makes it harder to get decidability results. Is decidable under resolution of singularity. And so the proof idea is that now phi is the wrong map, but we can still construct a map from a power of this, namely the nth power, in which maps surjectively to, well, the other way around. You can find a map from this thing to the nth power of this, but that's still okay. And then you use the fact that I said this is some math, and the fact that work by some people here, and I guess not everyone. Of course, we get names and theorems. And then is the Philip Dittman and Arix. That under that they also built onto work of Dana van Schouten, and they have a little better or like weaker version of this. We get that Hilbert stands problem over FQT, where we have the language T together with some order of T predicate, that this is decidable under the same conjecture.